My name is Buck Woody. I'm a data scientist at Microsoft. I'm what's called an applied data scientist. So what that means is I don't come up with new algorithms and things. I'm not in the back office doing the math. I'm usually putting it to work. So that's basically where I'm at with this. I work on the Azure data team, so SQL Server, Azure data, that sort of thing. And of course, the new Fabric stuff, working on that too. We're all working on Fabric, so it's all good stuff. And the co-pilots and all that. Worked with Joe Sack on the co-pilot. You saw how many of you were in the keynote this morning? Got to see it. So all the co-pilot stuff you saw at the end that I was demoing with Aaron, I was working with Joe's team. They did the heavy lifting. I was just there for comedic relief mostly. So what we're going to do today, we're going to understand generative AI, and basically we're going to take a look at it in the context of AI. This session is going to be more of an overview of all these things and demystifying all these things. Now, I have at the very end for you a PDF that you can download and you can pull it from the web, and it's got all the links and all these slides. And there's a lot of links. It's not a link farm. I've got stuff in there. I've been very careful about what we put. There's especially one that I usually love to cover when we talk about vectors. I won't have time to show that particular link today, but the link is in there, and you can play around with a vector simulation. We'll talk about those. We're going to talk about an overview of GPT, Generative Pre-trained Transformers, the processes and designs, and then we're going to talk about how you can actually use this stuff, and we're slanting that towards a data world. Does this sound like something we want to do today? Sounds okay? All right, let me put 50 on the clock, and we will get started. I use presenter view. If you don't do that, you should check it out in PowerPoint. Really useful. Let's talk about the introduction of artificial intelligence. It's actually an umbrella term. So artificial intelligence covers everything starting in 1956 is the generally recognized time for doing that, all the way down to machine learning, which we put about 1997. None of these things are that clean, by the way. The dates kind of move around a little bit depending on who discovered what and so on. And then we get deep learning in 2012, and then we move on to generative AI, which was largely born out of a paper called All You Need Is Attention by a team at Google. And we'll talk about each one of these and how you use them. All of them build on each other. That's the key to know that this is an umbrella term. So let's start out with the first one, which is artificial intelligence. There was a research paper put out in Dartmouth, a college in the US, and basically this guy said, you know what? You can define human intelligence so well, I know what humans will do so well, that you could pretty much write it down, and if you can write it down, you can make code, and if you can write code, you can make a computer do it. That was the belief that they had. Now, this has turned out not to be true. Number one, humans in the aggregate are quite predictable. Humans in the individual are quite not predictable. I can tell what a large group of people will do. I can't tell what you're going to do in a given situation. So this is largely not true. We started out doing this, by the way, this coding portion that a machine can be made to simulate it with what they now call, and I'm kind of sad because this is called good old-fashioned AI. Which is that's where I started, is now called good old-fashioned AI. We use various systems, symbolic systems, logic, fuzzy systems, simulation, expert systems. I'll show you how to code some of these in the booth session that I'll do down in the Microsoft booth. And something called evolutionary computing, which was kind of interesting. Now, expert systems are sort of a group of if-then statements. Right? You go to the doctor, and the doctor says, you say, my arm's hurting, and he's like, does it hurt here? No. Does it hurt there? Yes. Can you lift it this high? Yes. Okay, you've got a cold. Whatever it is that the doctors say. I don't go to doctors, so I don't know. But the idea here is these were quite simplistic, and they fell down pretty quick. So as we think about the next phase, this is where things become more interesting because we get into some of the more statistical methods. And the main ones we want to think about here, I want you to focus on inference, which means taking lines of data in the past and then seeing lines of data in the future that you'll predict out. Does anybody remember y equals mx plus b? Did I just send some of you into a flashback of high school when you got put in that locker or picked on by that kid? Remember that kid? And he picked it. You're nodding. You know what I'm talking about. You have to, okay, y equals mx plus b. That's the slope and the intercept. Remember that? So we could take numbers that we knew, and we could plug that into a formula, and we could project out what the next number might be. That's the basis or the idea of inferential statistics. And that worked pretty well. We get into some other things of information theory, which, by the way, was actually formed in the idea of understanding electronic signals and physics, but works for data quite well. But the big one at the bottom there is normative Bayesian decision theory. What in the world does that mean? It means to change the predictions that you have based on new information. That becomes very pivotal to what we're thinking about here. So Bayesian decision theory. You've probably seen bell-shaped curves and the tails. Remember that? Did you ever take statistics in high school or college? Take some of that? Remember, now you just had another flashback, right? You were still no more popular in college than you were in high school, and you thought it was going to be different, but it's not. Okay, that was just a diatribe. I had a rough high school. Okay, so this was the early days of artificial intelligence, and the newspapers and the magazines said, oh my gosh, AI is coming and they're going to take your job, and they had pictures of robots doing housework and so on. Turns out the robots are now doing all the poetry and music, and we're doing more housework, so I don't know how that's working out. But we had something they called an AI winter. What's an AI winter? Well, we had this big promise of what would happen, and it didn't happen. So the newspaper went, hey, there's no robots that do the dishes and vacuuming. This is terrible. I still have to iron my own clothes. I am still Iron Man. And so they went into an AI winter. It's all fake. Nobody cares. This stuff is useless. Well, it wasn't useless. We kept some of these ideas and we moved forward into a new era. And in between this, by the way, you'll see some things, data mining. How many of you have heard that term, data mining? Data mining is where you took larger sets of data and you begin to apply some of these algorithms that we saw in the past to walk over that data and begin to make some of the early predictive methods that we still use today. So what happened was some of the statistical methods and some of the early logic methods got together with data mining, and they had a baby, and this was called machine learning. So we're building here on those predictions. We get into algorithms and so on that we deal with. So let me run through a few of the more popular families of these algorithms. These aren't all of them, they're basic families. Now, the main one we use is something called regression. Remember that y equals mx plus b I gave you? That's a linear regression, a line that goes backwards, regression, and you can predict the future. There are other kinds. You can get parabolas and all kinds of other curves that make these predictions. So these are a family of algorithms that we can begin to use over larger sets of data. And as we begin to use those, what do we mean by use them over larger sets of data? Normally when we want something, we write a program and we say do this to the computer and it does what we tell it. However, in machine learning, we don't give it a program. We actually give it data and we give it algorithms that begin to work together to see how close am I getting to the target variable you want, and they will adjust themselves, which is really weird. And as they do that, they can then make predictions, and once trained, they're a model, which a model is kind of like a, don't tell any of the other data scientists I said this because I get in trouble and I don't want to lose my data scientist card, but basically an Excel formula. That's what really happens, right? That's the whole world that runs on Excel. Did you see, what was the headline I saw yesterday, this morning, that the F1 director came in, I think it was an F1 director, car racing, and found out that the entire F1 circuit is being run on 20,000 Excel spreadsheets? Anyway, that's got nothing to do with machine learning. Although you could do machine learning in Excel. That's a different section. But this idea of this regression, we give it the data, we show it this algorithm, we run it through, and we say, how good were you? We train it. And by training it, we just mean that it watches the output. We keep some data to the side, we call this test data, and we check its work. And if we like it, we go forward. If we don't like it, we can change some of the parameters, but we've renamed those. We call those hyperparameters because that way it sounds like you can make more money. No, they're slightly different. But we change those until we get the answer we want, and the algorithm is now considered trained. Keep in mind, with everything I'm showing you, all of these are a guess. All machine learning, all this stuff is a guess. And you have a certainty level. And if the certainty level is too high, you shouldn't trust it. It's kind of interesting. The better it gets, probably the more wrong it is. That's a true statement. And so you look for it to be balanced out to be mostly correct, but not completely perfectly correct, because then you've done something called overfitting, where you've only shown a certain kind of data, and of course it recognizes it because that's all you showed it. When it sees new data, it won't know what to do. Let's think about it this way. When you learned to read, they gave you a book and they showed you this is the see John run, see Jane run, and so on. You saw the little words, and then they showed you another book, and they showed you another book, and they showed you another book. And over time, your mind developed a model that when I see shapes that looks like that, that means that's a word, and this word means this thing. Now, you're able to not have any of those books, the training data, if you will, but you're able to read a book you've never seen. See how that works? Your brain works this exact same way. This is one of the algorithms we can use. Another one is something called Is It Odd? And when I teach college and I show this, I ask people, is this an odd picture? And they all begin to answer. And if you begin to answer right now, is it odd? You're wrong, because I haven't told you what normal is. If this is the contents of my desk drawer, this may not be odd. If I work in a new pencil factory, this is very odd. If I work in a mechanical pencil factory, this is very odd. Some of these things aren't even pencils. Colored pencils aren't pencils, they're wax, not graphite. So it all depends on the question, and that's important in data science, to ask the right questions. Another algorithm is called categories. And here we put classification. We put things into categories. We have binary categories, it's this or it's not this. Or we have multi-class, which is really just a bunch of binaries. It's this, it's not this, so it's this. It's not this, so it's this. It's not this, so it's this, and so on. And we can classify in that way. This one is reinforcement learning. If you've got one of those little sweepers that goes around the room and hits the wall, you know I'm talking about, the little Roomba things, that's actually got a very nice machine learning algorithm on it if it's from iRobot, which is the company that makes them. They make those for the military as well. And the idea here is it learns based on external inputs that it gets as it goes. I put the red wire and the green wire up there for reinforcement. Like if you cut the wrong wire, it explodes, and you're like, well, not going to do that again. I didn't know what else to put. Okay, because I couldn't get a Roomba. It just looked like a circle. Then the final one's kind of interesting. On all of these, I know the answer. You've got your textbooks, and your teacher says, no, you did a great job because you read the page correctly. She knows the answer, and you were learning, and she could correct you as she goes. But what if you don't know the answer? If I were to tell all of you to get into 3 categories as closely related as you possibly could right now, what would you do? Well, you can't do it by size or weight or gender or height, or it just, there's not an, you can't figure that out quick enough. But with a clustering algorithm, you can just throw some data on the ground and say, arrange that into 3 groups that are the most similar. Those are called centroids, the number that we pick. And so the idea, it can put them into categories. Why would you care about that? Well, customers. You ever rented a movie and customers who like this movie also like that movie? Well, you were part of a clustering algorithm. That's exactly how that works. By the way, when you clicked on those, please select all traffic lights. You're actually training. You're part of the training of an algorithm for machine learning. We use those in CAPTCHAs to train how to recognize a red light. And you always know why they use traffic lights, because they're making self-driving cars. It doesn't work, though. Anyway, that's the machine learning. So you can now put down on your resume, CV in Europe, that you know AI and you know machine learning. So you're an expert in that. I've just given you all that information. Now let's talk about deep learning. What is the DL for deep learning? Well, it's modeled after the brain, but I want to stop right here and say in very clear terms, no machine learning we have anywhere it resembles anything that's happening in your brain right now. The connections that you have at 5 years old vastly outnumber anything we can even remotely think of right now. So it doesn't work like a brain, we just patterned it on the brain. Having said that, I take a piece of data that looks like a Rubik's Cube, okay? I take the Rubik's Cube and I knock the first layer off and it falls down. I take the second layer and I knock it off and it falls down. I now have a line of Rubik's Cube slices. You with me so far? I take all of the slices and I turn them this way so that now I have a bunch of small cubes that represent the Rubik's Cube if I were to put it back together. You with me so far? That's a tensor. And we have libraries, things like TensorFlow, that can deal with those. Those become inputs. And perhaps they have to do with color or shape or size or whatever they happen to be. But I take the data and I push it into a tensor, and I can begin to push it into these input layers. Then there are a bunch of layers after this, and there can be lots of them, and we just call those hidden layers. The reason we call them hidden is because we don't know what they're doing. It's like those pachinko machines where you put the ball on the top and it hits all the little nails on the way down. You cannot predict where that ball's going to be. Interesting statistic, you can put a bunch of balls in there, it will always make a bell curve. But you cannot predict where that ball is going to go. You just don't know. Same kind of idea. At the end, you get the outputs, which is, what am I trying to train on? Let me show you what looks like inside of one of these. Don't make that face. I'm not going to make you learn math right now. But the basic ideas here, we have these inputs. Now, I left something out. We have something called weights. And again, we like to make up new words so that it sounds more impressive. These are just parameters and numbers we put on top to sort of favor the algorithm to get the right response. It's sort of a cheat code, if you will. And we fiddle around with those until we get the answer we want. In the middle is something called an activation function. What's an activation function? This says, I need you to send this to the next layer or don't. That's what it does. It sends it to a few of these, and it can be a directed graph, which you see here, or an acyclic graph, which goes in a different way, or it can also be a redundant graph. But the idea is it sends to each one of these. I think I'm using a sigmoid here. Yeah, the sigmoid is my activation function. There's a bunch to pick out which one happens, and I get my output on the other end. What does this look like in real life? Let's take a look. A little more complicated, yeah? But the idea is we have our input layers, which is our face, and we break that apart. The layer that comes in next maybe detects maybe edges. And the one that follows that detects combinations of edges. And perhaps the one that follows that has some object models like noses and eyes and teeth and hair and so on. And at the other end it says, that's a picture of a lady. That's basically the way this works. Now, if I train it on lots of different pictures, it can tell me what this is probably going to be. I could train it on pictures of people like Bill Gates, and it would tell me, I think that's Bill Gates. And it would be right. And there is a detector inside Azure that you can get that will actually do exactly that. Recognize landmarks like you're in London, you're in Paris, and so on. All right, this is how deep learning works. The reason it's called deep is these layers are normally not shown like they are here horizontally. They're normally shown vertically, so they go deep. The interesting part is we don't know what's happening in those hidden layers. We don't know. It's almost impossible to measure, and it may not be the same every time. Everybody with me so far on machine learning? This is really good with graphics and so on. It does a great job, but it doesn't do everything. So let's move forward. The next really important and really fun thing we need to look at is something called natural language processing. And we're using all of the things that came before NLP to show you how NLP works. So all of those things are embedded within this. Here we go. So we have a deep learning model, just like you saw a moment ago, but it's got some phases. So I've driven out the phases here for you so we can walk through them. And the first thing, we get our data. We call this, by the way, again, we have to rename everything. It's called a corpus, which in Latin means body. And it's just a bunch of text. We get a bunch of text. We could do with this graphics as well, but it's a bunch of text. So we get our corpus here, and the first thing we need to do is normalize our characters. I don't know if you've seen languages that are not English, but some of the German languages have little dots all over things. Have you seen this? It's very odd. So anyway, we normalize those, and we don't just do that, by the way. We have German models, and we have French models and all the rest. But the point is, you normalize it into whatever you're trying to get. Then we do something here called tokenize. What in the world does that mean? Well, we begin to add numbers to mean a word. When you see a letter or the word CAT for cat, let's say, you have a picture in your head of that. You actually recognize the artwork of the letter C, the artwork of the letter A, and the artwork of the letter T. Your mind then changes that to a different set of artwork that looks like a fuzzy cat. So you're actually tokenizing in your head one thing for another. Once I tokenize that word, and I've got a number for it, I can begin to do other things that have to do with language. Stemming. In fact, the word stemming has a stem in it. We take the fronts and backs. You remember gerunds and things? Oh, first we had math, then we did science, and now we're doing English. Some of y'all are just like right now having flashbacks of high school. I promise you I won't do any more English. Well, we'll do one more. We have lemmatizing, which is another English way to break up the word, and then we get rid of stop words. There are certain things we don't care about. The, and so on. We just don't care about them. Okay? So we get rid of those. Next, we move to something we call feature creation. Features are merely columns of data that more accurately describe what you're trying to understand. So a feature might be I'm wearing black shoes and gray pants and a gray jacket and a hat and so on. Those are features of the Buckwoody object that you're trying to describe. So we need to create the features that we can work with. But remember, we're working with math. And so we take these things we've done with our tokenization and we create numbers out of those. These are called encoding or embedding, that we make large sets of numbers that mean the word. But keep in mind, it can be part of a word, right? It doesn't have to be the whole word. Maybe it's the stem of the word. So there's lots of numbers going on in here. And there's going to be a lot of measurement of these numbers as we walk them through a deep learning model, the one you just saw. So as we do this, we begin to think about things called vectors. And we'll talk about vectors here in just a moment further. But a vector is simply a three-dimensional point in space. So we've got an X, a Y, and a Z, right? We remember X and Y. That's like this. The Z goes this way, this way, this way, this way. Well, think of not just 3 dimensions, but lots of dimensions, maybe thousands of dimensions. As we begin to calculate these vectors, I can take the numbers that I had and get a vector for that. And I can take another word and I can get a vector for that. Keep that in mind. That becomes very important. Then we run it through our model and we try to say, when you see these things in this arrangement, that's what this means, okay? And that's our evaluation phase. We call this, by the way, tuning the model. When you hear in data science that something is a well-performing model, it doesn't mean it's fast. It means it does well. It does the right thing. It's working. And then when we're done, this is kind of interesting, we need to retrain it. Most of us write software, we deploy it, and we're done. But in machine learning, you deploy it, and then you say, click on all the things that look like a traffic light. And you actually retrain it. You're like, okay, let me put that back through the steps and train the model again. So we do quite a bit of retraining as we go. What this allows us to do now is begin to recognize the way words work together. Let's talk about this for a minute. We all know what royalty is. Yes, everyone knows what royalty is. And we know that you can have a king and a queen and a prince and a princess. We know that we can have a king without a queen or a queen without a king. We know that. We know that for a princess to be born, though, we need the queen, right? That's the way that works. And so we begin to make these relationships in our head. So if I were to say to you, Princess so-and-so, you would immediately associate in your brain things like king and queen and royalty. You would associate those. You would associate perhaps female. You would associate perhaps castle and so on. All of these associations you're making would have basically some strengths associated with them. So if I hear princess, I might hear castle. So she lives in the castle, but she doesn't own it yet. So perhaps it's a weaker relationship than queen and castle. Guess what those relationships are? They're vectors. They're simply vectors. Now that I've got math and these embeddings, I can begin to store. And you're probably saying right now, wait, are you saying that we store all of this, all of these numbers? Yes. This is why you need a special system to process that math very quickly. And you know what does that really well? You know what processes polygons really well? GPUs, graphical processing units, which we didn't even care about in the early 80s, late 70s, early 80s. Didn't care about GPUs at all. Who needed graphics? You're writing Word documents. You don't care about that. You need email. You need to calculate some math. But then gamers came along, and artists came along, and they said, this is too slow. I can't show my cool graphics on the screen. And so we invented some new chips, and we said, okay, you're not going to do what a CPU can do, a central processing unit, but you can calculate polygons. So computers, by the way, computer screens can't make a circle. They just make a bunch of polygons really close, and your eye thinks it's a circle. But it's still a polygon, multi-sided shape. So if I can calculate these polygons, everything on a GPU is a polygon, if it can calculate numbers and angles, hey, that's a vector. And so GPUs become incredibly important when we start working on these things. The GPUs that you have in your system at home, your gaming system at home, are not the ones I'm talking about. I'm talking about the ones just before NVIDIA released another one that's incredible. The ones that we need, that we'd like to use, the scientists like to use, are $40,000 each. And I need several 100,000 of them if I can get them. So I go to Bill Gates, and well, he's gone. But anyway, I go to Satya, and I say, hey, do you have any spare change? I need several hundred $40,000 GPUs. Meanwhile, all the tech companies are doing that, and the chip makers are working as fast as they can. And then NVIDIA announced a couple days ago one that's 30-something times faster and 17 times less power that they need, and so on. This is the new frontier, is these GPUs. Or now they have AI chips. Google has a Tensor chip. My phone is one of those Pixel 8s, so it's got that in there as well. This allows us now to understand language. When you talk to your phone and you say, what's pizza near me? It understands that because of this. Is that incredible or what? But wait, there's more. Now let's go to the big guns. What are we looking at on time? Oh, we're doing real good. You're meant to understand and memorize all of this. I've got a transformer architecture, and then I've got a BERT and a GPT. Let me explain kind of what that does. I'm going to try my cool new toy. I don't know if it's, oh, it'll work. Kind of. No, I'm not going to do that. All right, I'm just going to point. So what we've got here is these are deep learning networks, specialty kind of deep learning networks, and there's some salient portions in here that are important to understand. And I've got some really good resources for you here. So basically, large language models, this is what this is called, an LLM. The GPT is one kind of that. Large language models, there's a few others that don't use these same components. But in a large language model, you send it an amazing array of data, like a lot of these corpuses, like the internet, like all of it, like every book review that's been published, every play that's online, every public domain library book, every chat you've ever had in your chat windows, everything it can find, and it begins to encode all of that text. Just like we did with the previous natural language processing modality, it does all of that and encodes and then gets vectors between them all. It's stunning to think about, but that's how it works. Once it does this, that's that first portion here that you can barely see here. That's the first portion here on the left at the top. That's called positional encoding. It then sends it through something called a feed-forward network, which takes what it got, learns a little bit, and sends it forward, and sends it forward, and sends it forward. In the middle is an interesting, by the way, it encodes these things into these vectors and these things that it can use to process the rest. This is from there, it moves it through something called a decoder, because the trick is in the name, generative AI, generative pre-trained transformer. This is the transformer you're looking at. A generative pre-trained transformer doesn't just understand language, it can turn around and make language. It can begin to say things. It's not saying anything. It looks at all the words it's learned and how they're related, and when you ask it a question, it takes that in, does the NLP on it to figure out what you're asking. That's called a prompt. And then it turns it through this and goes, oh, okay, tell me a story about a king and a queen and a princess on a picnic. and it knows what a picnic is. It knows the vector for that, and it knows picnics have food, and they're outside, because it sees those words often together, and it sees that you've got cake and tea and whatever it is you take on a picnic, and it knows what a king, and it knows what a queen is, and it knows that when you go on a picnic, you have a car. So it says a king and a queen get in the car with their princess, and they drive to a local park, and they have a picnic with cake and tea. And you go, wow, it's magic. It's not magic. However, it works a lot like your brain does. That's how you would think about it too. So while it's not using the same methodology of your brain, you get a similar result. Here's what's interesting. This starts appearing magical to us as we begin looking at it, because we think in a language, right? We have computers that do graphics, and we're like, wow, that's cool. And we have computers that can compute numbers very quickly. Wow, that's cool. And we have computers that can do WordPress documents or whatever. And we're like, that's amazing. But when it can talk, we're like, oh, it's intelligent. It's not intelligent. It's putting words together. It's kind of like a very sophisticated set of autocompletes that can understand what it's been auto-completing. And it also randomizes. So if you ask it that again, part of the transformer architecture, when it does the decoding, it will actually send it back through and say, well, don't always make them go on a picnic to a park. Make them have a picnic on a beach. So you get a different story if you ask again. Does that make sense? The prompts are very important. You never called a support line in another country, not your own country, and you're talking to someone, you're trying to make them understand what problem you're having, and you realize very quickly you're not communicating, and you begin to back off and try different ways to say how they can help you. You know what I'm talking about? It's exactly what you should be doing with ChatGPT. You should learn the art of prompting. Doing things like, you are an experienced marketing professional. Create a marketing plan for my cool new service called so-and-so. Return the result as a table of items I should do, and take your time. You can tell it, take your time, and it will. It will get better if you tell it to take your time. And you can tell it things like, cite your sources and provide examples, and it will. Prompting is the number one thing you need to learn. It is the number one thing, because you're talking to the system. Now, GPT 3.5 needed way more help in prompting. 4 doesn't need as much, and 5 is in works. So the more we do this, the more it's going to figure out that you don't have to prompt it as much. When you ask it about marketing, it will act as one. But you can tell it now, act like this, do this for me in this way with this result, and then any other instructions. Do not include this, do include that. Prompting, super important. So there's a couple of ways to do these. GPT, generative pre-trained transformers, work like the one on the left. The one over at Google uses BERT architecture, so it's just quite a different, mainly the difference is the classification layer and how they work with those and their embedding units. And I've got resources for you to learn more about that. Now, we mostly train, like the natural language processing was on language. We had the graphic on the deep learning, and it can do graphics, right? These are called narrow AI. They do one thing. They recognize red lights or whatever it happens to be. But a generative pre-trained transformer, or just an LLM, creates something called a foundation model. What's a foundation model? A foundation model has been trained on lots of data, and it can be applied to more than one thing. That's the important part. You can have it answer questions or get sentiment. Because it understands good and bad words, you can say, was it a good picnic? Is that a good restaurant? And it will know the word, I didn't like it, or this was terrible, or whatever. It'll know that that's bad, so it can give you sentiment. You can get information out. Where's the restaurant located? Image captioning. Can you take a look at this picture and tell me what words should be under it? A prince and a princess on a picnic. Instruction following. Code generation. This is kind of interesting. Back in the GPT-2 days, code generation was done with something called a codex, meaning it was a special kind of AI that if you asked it about code, it went and did just that. The models got so good later, from Stack Overflow and all the rest, you trained it on all your code, and now it can generate code when it's just like, to that, it's writing English. The other thing that's interesting, it can do summarization because, again, vectoring. and image generation. But one that's really kind of interesting is it can translate. If I train it on German, and I train it on English, and I train it on French, to the computer, they're all just a language. So I can say, translate this into French. It's like, okay. And it will, because it can do that with this. This is what's interesting, though. Foundation models began to act in a way we, data scientists, didn't quite understand. It began to do things we didn't program it to do. It literally created something called emergent behavior. All AI now has emergent behaviors. These are things we didn't think it could do or realize it could do, but it can do. The translation part, we didn't know it could do that. And then it said, yeah, I can do that. And we're like, you can? And our users were telling us, did you know it'll do physics? And we're like, well, I mean, I know it can write, a book that has physics terms. No, it can do physics. No. Yeah, watch. They were showing us what our models could do, and you still do. You're still showing us what it can do. It's pretty impressive. These parameters, by the way, these billions of parameters, we've blown way past that. This is old. This graphic's like 8 months old, so it's ancient. This is ancient history. Now, the interesting thing is, when we come to this, we begin to think about things like, well, is this real? I mean, you've said that it's just basically a big autocomplete. Is it really that real? Well, we can train not only text, but we can train other things like pictures or sounds. I can now get your voice for 3 seconds, and I can have you make a phone call that sounds just like you in 3 seconds. I could take a picture of you and make it look like you're walking, just from just a few samples of the data. So is it just a fad? Well, a couple of years ago now, we asked Midjourney, which is an AI that can draw pictures, to draw a picture of a young blonde girl in a field of flowers. That was the prompt we gave it, photorealistic. And this is what it created. Now, she's got like a third eye on her nose, and it's not bad. It really isn't bad. 13 months later, we said, let's try that again. And the same prompt made that. So you tell me, is it all just fake? Who cares? This is all just hype. This isn't even now. Most of you have seen Sora by now. Sora is a new model that's come out from OpenAI, and they're not the only one, that can take a text description of a movie you would like, and it will make it for you. Now, it only does like 60 seconds right now, because that's really, but you can say a race car driver wearing a red suit, driving around a track, and he almost hits the wall, and it will make a movie for you out of that. Now, Sora hasn't been released to the public yet, but there's a couple of other generative movie AIs that have, and there are so many generative AIs. So, now that you know how it works, you're experts in artificial intelligence, you know machine learning, you know deep learning, you understand natural language processing, and you're now an expert on LLMs or GPTs, whichever one you want to put on your resume to sound better. Let's go and figure out how you can actually put this to work. So first of all, at Microsoft, and that's what I'm going to talk about because that's where I work, there's lots of tools out there, but the one we use, by the way, if you're using the Edge browser or if you just go to Bing and you go to the chat feature, you're using GPT-4 for free. So you can use it today, right now. You can use it. You should try when you get started, and I'll tell you more about how I work my day in doing this. But you can start with Azure AI Studio, and we have all kinds of pre-built things for you, speech, vision, language, and so on. And then we've got all kinds of other things that we offer in the generative area. The next one you can think about are the different open AI services we have. Now, you can use something where it's called RAG, Retrieval Augmented Generation, and basically you can take your own data, and this thing's been trained on the internet and knows how to talk, but you can let it look at your data and have it make predictions from that. Internal to Microsoft, I can now switch to our private internal thing and say, hey, who's working on the XYZ project and what are the basic features of that? It will walk across all of our documentation and show me that in the screen, if I'm allowed to see it. And by the way, I'll talk more about Do we use your data? Are we being careful with this stuff? I'm going to give you a whole section on that because it's important. We have plugins so that you can also begin to add in new features and functionality. We have content filters so you can make sure people don't ask the wrong question or that they don't get data they're not supposed to have. We also have these various models, and by the way, GPT-4 is already GA, 3.5 is available, ChatGPT is available, and our image generation is DALL-E, which works very similar to the Midjourney stuff. We have tons of co-pilots, and we think that's important to say co-pilot. It's not the pilot. I don't want an AI doing anything, but I want it to tell me about things. That's the way I use it. I don't have it just do things. These are the co-pilots, and they're incredibly useful. This has replaced all my friends I used to have. It's not true. That's not true. I've never had any friends. High school, it was really... so anyway, these chat can be very useful. You've written chatbots before, perhaps, using your own code, and so very hard to work with. Now you just plug them in, and they're good to go. We have a GitHub Copilot. So within Azure Data Studio or other tools, if you have Copilot enabled, you can begin to tell it, you can't really see it here, but basically I've got a selection, and then I say in just a comment, pivot that query on token color for purple, blue, green, yellow, and rename the column to match the colors. And it literally will know that query. It's context sensitive, and it can go find these. It's incredible. I use this all the time. I do not do any task right now. I don't do any task right now without opening ChatGPT first. It does not do my work. It just gets me started. I don't know where to start. I can just ask it. It's an expert on just about anything. Trust but verify. It may not be correct, but it gets me started. I do everything in ChatGPT first. Everything. And then I come back and fix it. Now, you can't just blindly trust it. I always tell my students at college, pretend that it's a 9th grader and it's doing your homework for you. Would you just turn that in college? Would you just turn that homework in? Would you check it real quick? You might want to do that. So it's a 9th grader you have to grade. It's an incredible tool. I highly, highly recommend you're using Copilots, and especially the one in GitHub. Let's talk about SQL Server and the databases themselves. SQL Server on-prem and in VMs has something called SQL Server Machine Learning Services. This is a subsystem within SQL Server that can run Python or R code. It's got T-SQL for your data work, so you can select things out of your database. And then it's got the ability to call out to Python code or R code and do things with it. Let me show you an example. And by the way, I have this aka.ms SQL OpenAI. You can see this notebook, this Jupyter notebook. You can have it. You can run it yourself. It will work. Basically, what I did here was I went into AdventureWorks, our sample database. I found a bicycle that I liked, and I said, you are an experienced marketer. Generate 2,000 letters of ad copy for this product. And all I give it is the description of the product, and it makes a whole sales pitch for me. So now I can run that on hundreds or thousands of these. The 100 or so I ran in here cost me 4 cents to run. 4 cents. I don't know what that is in metric. How much is 4 cents? Do you know, Ann? Do you know? You have no idea. No, not 4 cents. Like, what is it in the euro thing? 4 cents? I don't think they have cents. I don't think they call it cents. Anyway, it's really cheap. 3p. That sounds disgusting. We should ask ChatGPT. How much is 4 cents in p? No, I probably won't say that. Anyway, I have this idea here. It goes and does the select statement. It turns that into part of the prompt. It sends it to ChatGPT, and it comes back, and it can even store that result in the database. Now I can show that to the marketing person and say, does this look all right? They can edit it, boom, out the door. It's done a lot of their work for them. Has it done all of it? No. By the way, I could also call out to DALL-E and say, make me a picture of that bicycle from the description, and it will. Impressive stuff. So this is one way you can do it. We actually have other ways of working with OpenAI. On SQL Azure, on Azure SQL DB, we now have the ability for you to call out to a REST, R-E-S-T API. A REST API is simply a representational state transfer API. It's HTTP, basically. You ask it for something, it comes back on a protocol. You can talk to anything, including OpenAI. On Azure OpenAI, you actually get this available to you. Oh, and I've got a link down here for the API builder if you want to see it. And again, I'll give you a link in a moment. The only one you really need to copy down is the one I'll show you at the very end. We're getting close to the end, but I did want to tell you about this. We really, really, really take AI serious. We have a thing called responsible AI, or RAI, at Microsoft. All the products I work on all day long, I have to get an RAI red team to attack it and see if they can break it. It's very important to us to do this. First of all, you need to understand what Azure has, Microsoft Azure. There's things you do, there's things we do to keep your data safe. But we do all kinds of things just to protect you because you're in Azure, no matter what service you're on. Secondly, we also have some things that I want to read out to you. Your prompts, inputs, and completion outputs, your embedding, and your training data are not available to other customers. They're not available to OpenAI. They're not used to improve our models. They're not used to improve any of our services. They're not used for improving OpenAI models, even used in your own resource. Your fine-tuned OpenAI models are available exclusively for your use. The service is completely controlled. The OpenAI service we run is controlled by Microsoft, not OpenAI. They give us the stuff, we run it. Does that make sense? Bear with me here. Our terms of service do not interact with any services OpenAI provides. If you train your own data on it, that stays with you. We don't know about it. We can't see your documents. And we're very careful about what gets what we do to protect ourselves. Just so you know, we get, what was the last number that I can say? I think we get over 1 trillion attack signals a day at Microsoft.com. 1 trillion. We have entire teams that do nothing but protect our firewalls and so on. So we try to be incredibly careful about this. All right, here we go. Last slide. This one you can take a picture of if you want. Number one, AI automates tasks, not jobs. You should not think that AI is not going to take your job. I can tell you what is going to take your job. Somebody who knows how to use it. So you need to be that person. Trust me, right now, it's a given. That is a cherry topper if you can say to somebody, I understand how this works. I've researched and read about it. I've used it before. I can show you I can show your people how to use it. I do something called an augmentation automation matrix. I take the tasks I do, write them down in Excel, the world's database. And then I have a column that says augment and another one that says automate, and then I put cost. And I put down, how could LLMs, how could generative AI augment the task I'm doing? How could it automate the task I'm doing? And then how much would that cost me? I've got some resources here for you. tinyurl.com, BWoodyGPT, that's going to be the document you just saw, the entire presentation with all of the links. Those links are curated, and there's some really good ones in there called out. Next is the Microsoft.com AI, pretty simple, but I put it up here anyway. This is all our resources for AI in one place. And then I'll give you a little sneak peek of the notebook I'm going to show in the session at the booth. And if you go to BW presentations, it's the one marked AI, ML, DL, NLP, LLM. And it's called Covering the TLAs. The 3-letter acronyms, and some of them are only 2. I know that. Don't tell me that. I know that. So anyway, those are there. Any questions? Do we have time for questions? We have 3 minutes. You got something? Yes. When is the session? I have no earthly idea. ChatGPT, when is that session? It's listed down in the booth area. I'm sorry, I just didn't. I'm working on no sleep, so I show up when I'm told. I've been married for 48 years, and my wife says to do stuff, I just do it, right? So she's not here, so I have no idea what time it is. Other question? Okay, great. Was this useful? Did you find that useful? Okay. Then that is a win.